Okay, let's dive in. Where has the time gone? One more week to go. We are going to talk this morning about the final project. We'll go through the actual document. My apologies, a little boring to read along together, but I just want to make sure we're all literally and metaphorically on the same page. Okay, let's do that now, actually. So there are two components of your final project, both of which are due to be submitted on Brightspace a little less than a week from now, by Monday, by 11:59 p.m. You're submitting two elements to Brightspace, a written report covering what you did for your final project, and a 2.5-minute YouTube video, which is going to be your oral presentation, which you will talk over and narrate live here in class starting at 7:30 in the morning next Tuesday. Again, I don't pick the exam times, so apologies for that. Okay, so by 11:59 p.m. on Monday, please find in Brightspace the written report submission, and you will be uploading one PDF document. Please make sure it's a PDF document. Minimum length 4 pages, double space, 12-point font, and in that written report, you're going to review the results of your A/B testing for us. So what are you currently doing? Hopefully what you are currently doing now is testing two versions of your final project, variant A and variant B, and you are looking for one of three possible outcomes by next Monday at 11:59 p.m. Either you're going to have evidence to support the fact that A is better than B, or you're going to have evidence that B is better than A, or you're going to have evidence that there is no difference between A and B. I hope for you don't get the fourth outcome, which is here's how fitness improved with variant A, and here's how fitness improved with variant B. Is A better than B? B better than A? No difference. Who knows? So whatever it is you're doing between now and Monday, make sure that you collect sufficient data to try and prove one of those three outcomes. Okay, let's imagine maybe this morning this is the data that you currently have in hand. You've done one run of the parallel hill climber or the hill climber or whatever evolutionary algorithm you have, and you have fitness plotted of the parent in the population or parents in the population over some number of generations, and you've got fitness on the vertical axis. For you, maybe a greater value of fitness is better, perhaps a lower value of fitness is better, doesn't really matter. What do you do if this is the current result you have? You've done one evolutionary run of A, one evolutionary run of B, and you're currently sitting in the fourth box, which we don't want you to be in, which is you don't know whether A is better than B, B is better than B, or there's no difference. Hopefully this is a no-brainer.
Run it for longer.
Run it for longer, okay. Now what?
Did you just change something?
We could change something, then you'd have C on your hands. We're still trying to test A and B.
You run it more times.
Run it more times, yeah? So hopefully at this point, your final project doesn't require too much brain power from you. Just collect more data. But it's a good question, what kind of more data is useful? You could run it for longer. You could go back and do a second run of variant A. A second run of A. So starting from a different initial random population of robots, you evolve A again. Now you've got one run of A, a second run of A, one run of B. We do another run of B. And get this. Is A better than B? Is B better than A? There's no difference between them. Or fourth outcome, we don't yet know.
We don't know.
We don't know yet. So what do we do? Let's do a run. Here's a third run of B, a third run of A. Just collect more and more replicates. I realize not everybody has the same laptop with computational ability, so it's perhaps not immediately clear how much data you can collect. Assuming you have a relatively robust laptop, you can set it up to collect data overnight. How many nights are there between now and Monday? That's how many runs you can get. How many generations do you run things for? It may be that at the beginning, there's clearly no difference, but with enough data, you start to see that in general, A tends to be better than B. I cannot tell you. It depends on what your A and B is. It depends on what your evolutionary algorithm is. It depends on how hard your fitness function is. Difficulty meaning how difficult is it for the evolutionary algorithm to start to make progress on your fitness task. If you're not sure, come and see me or the TA later this week and we can talk about it. That's what you're currently doing. Okay, so that's what I mean in the document by you are currently performing A/B testing, by performing multiple runs of A and B, allowing each to run for the same number of generations. When you eventually try and defend the claim next week that A is better than B, for example, in this case, A is better than B, we want to have the same population size and the same number of generations. You want to have allowed the evolutionary algorithm the same amount of computational effort for A as it had for B, right? That's fair. If we ran B for twice as many generations, that's a little bit of an unfair advantage for your variant B. Okay. You're then going to generate visualizations to try and visually prove to us which, if either variant, produced better robots. This is not a statistics class, so you don't necessarily need to provide error bars or confidence intervals if you know what those are. That's a statistical method for really strengthening your claim that one group is doing better than another. A set of fitness curves where we can see that generally A tends to do better than B. For example, this would be visual proof of whatever your claim is, assuming you have enough data. Yeah? Okay. All right, so that's generally what we're looking for. As you're performing your A/B testing this week, I suggest you write your written report along with your collection of data, so you're not writing your written report all at the end. Your report should contain 4 sections, about 1 page per section. Points will be deducted for poor writing quality. We want to make sure you communicate your ideas clearly to us. Okay, let's go through these 4 sections. First section should describe your goals. What projects did you tackle during the deliverables? How did you create A and B from that project? What was the question you tried to answer? In my cartoon example here, for me, perhaps A was the quadruped that you have at the end of assignment 10, and maybe B was a hexapod, and I wanted to see which one could my evolutionary algorithm evolve a faster gait for. When we finish reading the first page of your report, it should be pretty clear to us what A and B is. It should be pretty clear to us that it's a fair comparison between A and B. When I created my hexapod, I could have created my hexapod to be 10 times the size of the quadruped. When I evolve controllers for that quadruped and that hexapod, guess which one's going to do better? The hexapod, because it's 10 times the size, it's more likely to cover more ground. That's an unfair comparison. So when you're describing to us what your A and B variants are, how much detail do you give us? You give us enough detail to understand what A and B is, and you give us enough information about variant A and B to hopefully for us to conclude that it's a fair comparison. Make sense? Okay. Second section or second page should describe implementation details. How did you code up your deliverables and your A to B test? What was your strategy? Please here describe in words. Do not copy and paste code snippets. Yeah. For some of you, this implementation details might be relatively straightforward. So in my case, I added 2 legs. Both legs had the same number of degrees of freedom as the legs in the quadruped. Each of the 2 joints in each of the 2 additional legs in the hexapod have the same joint axes as each leg in the quadruped. It's not going to take me a page to describe all that. For some of you, your variant A and B requires more explanation. You're going to need at least a page to describe it. We're not necessarily looking for exactly a page of implementation detail. If it's less than a page, you can provide us with more detail in some of the other sections. Okay, third section, third page should provide some results from your A/B test. Most importantly, you should demonstrate that evolution did in fact occur. Show that an evolved robot did better than a randomly generated robot. That's the first piece of evidence we want to see in your results. Have a look at my cartoon example here. Did evolution occur? Did the quadruped evolve to move further than randomly generated controllers for A? I see a lot of you nodding your heads. How do you know? What is it about this picture that's convincing you that evolution did in fact occur?
Fitness value.
Fitness value went up, right? How much does it need to go up in order for us to conclude that? Again, that's up to you. The more replicates you have of your runs, the easier it is to see. You might get into a situation where it's very difficult for evolution to make progress. You might get a fitness curve that looks like this. Did evolution occur? Hard to say. You do a bunch of runs, and if they all tend to look like this means that, yes, there was a little bit of evolutionary improvement. It wasn't much, but there was some, right? This difference here is known as the effect size in statistics. So if your effect size is small, meaning it's hard, in your case, for your evolutionary algorithm to increase fitness, you're going to need to collect more data to prove to us that evolution did, in fact, occur. Alternatively, if evolution is able to make quite a bit of progress, you don't need many replicates to be able to prove that evolution did in fact occur. So many of you have asked myself in the TA, how many replicates of A and B, or how many runs of A and B do I need to do? Our answer is always, we don't know. It depends on what your final project is. Okay, so that's the first thing we're looking for in your results. Then we want to see, did one variant do better than another, or did both produce about the same quality of robot or same quality of behavior? Okay, so what we've been drawing here are fitness curves, how fitness changes over evolutionary time. This is probably a necessity. This is something we're going to want to see. You can additionally include some of the many other ways of visualizing what your evolutionary algorithm did that we've seen throughout this course. When we taught in the lecture on legged locomotion, we looked at one of my old projects where I included some fitness graphs, which didn't show how behavior improved over evolutionary time. It showed what evolution produced. What did the gait actually look like in those legged robots? We saw some phylogenetic trees. So this shows in an evolving population of robots, how are they related? Are there different species that evolve? Are there extinction events that occur? How much variation is there in the behavior or possibly the morphologies of the robots in your evolving population? Okay, visualizations of how robots evolved in one environment do when they're exposed to new environments. Some of you are evolving your robots over flat ground and then transferring it into an environment in which there are obstacles on the ground or there's rugged terrain. How would you visualize that? How would you visualize robustness? How well or how poorly do robots evolved in one environment do when they're exposed to a new unseen environment? Okay. And because we're roboticists, we love to see cool screenshots of your robots, what they look like, how they move, also fine. These are all optional visualizations. I would consider fitness curves necessary. It's going to be hard for you to prove what we want to see in this section without fitness graphs. For those of you that are comfortable with statistics and know how to compute confidence intervals and p-values, knock yourself out. We're happy to review those as well. If you don't know what a p-value is, you don't know what confidence intervals are, that's fine. We're not expecting it. Try and convince us with more data. In Origin of the Species, Charles Darwin, there is no p-value anywhere. There is no fitness curve in that book anywhere. How did Darwin convince us about what was going on out there? Hopefully some of you have actually read the book.
A lot of anecdotal evidence.
A lot of anecdotal evidence. When in doubt, drown the reader, which in this case is me or the TA, in data. The more data, the better. Yeah? Okay. Okay, like I said, grades will be deducted if it's unclear whether A was better than B was better than A, and there was no difference between A and B. I'm sorry, I realize I'm being repetitive here. We don't want you to try and get the quadruped to do better than the hexapod. That's not the game we're playing here. You're trying to reduce the chance that you're going to end up with uncertainty at the end. I don't know. All good? Any questions about any of that? Okay. Fourth and final section of your written report, you're going to verbally demonstrate to us that you've thought carefully about your deliverables and your A/B test. What was surprisingly difficult? What was surprisingly easy? What did you learn along the way of your final project about physics engines, evolutionary algorithms, how to conduct an A to B test? Tell us what you learned. I realize some of you are taking other courses. There are other things that are impinging on your time and attention and possibly on the computational resources of your laptop. So we're taking all of your work with a grain of salt. But if you did have another year to work on this project and I gave you access to the supercomputer, what would you do with it? How would you take your initial test and redo it in a better way with more data? What did you learn? How would you do it better the next time? What new features would you want in PyroSim to make things easier? Again, you're not using the most high-powered physics engine, so a lot of you had ideas that were difficult to embody in the physics engine you had available. What aspects of this hypothetical expanded project do you think would be relatively easy and which would be difficult? Okay. That's what we're looking for in the written report. Any questions?
What style does it have to be? Like, do we have to write it like paper style?
Not paper style. The format that's written here. That's all we want to see.
Okay.
Yep. Doesn't matter. LaTeX, Word document doesn't matter formatting. But at the end, we want a 4-page PDF, double-space, 12-point font. If you run long, that's okay. We're happy to grade a 5-page PDF, a 6-page PDF. Please don't send us a 20-page PDF. Freya and myself also have a lot of things going on next week. Keep it within reason. Speaking of paper formats, I will say that I've seen several weekly reports that look like they could become actual new results that have not yet been reported in the robotics literature. If you think you have something like that on your hands, come and see me. You might also see an email coming from me or Freya indicating we think you might have a paper on your hands. We would love to help you expand some of your final projects into actual publications over the summer or next fall if you're still going to be here. We're happy to do that. Let us know. Okay. There are 60 final projects, so it's hard for us to keep track of everything that's going on. If you think you have something promising, let us know. Okay, written report worth 7% of your final grade. Second part is the oral presentation, which is also worth 7% of your final grade. The YouTube video, which is the tangible part of your oral presentation, you need to submit it to Brightspace by 11:59 p.m. next Monday. Okay, what are you submitting to Brightspace? You're submitting a URL that is going to point to a public YouTube video. It needs to be public at least for Monday night and Tuesday morning so that we can stitch it into a YouTube playlist, and that playlist will play here in class Tuesday morning. Okay. There are 60 of you in this class. We have 2 hours and 45 minutes on Tuesday morning for the final exam period. That means each and every one of you has no more than 2 minutes and 30 seconds to orally present what you've been doing over the last month. Not an easy thing to do. Okay. If it's 2 minutes and 23 seconds, okay. If it's 2 minutes and 37 seconds, okay. If it's 2 minutes and 41 seconds, not okay. We got to get through 60 of these oral presentations in 2 hours and 45 minutes. So my apologies in advance. We're going to be very strict with length limits with your oral presentations. Fair? Okay. All right. So what are you going to be putting into this 2-minute and 30-second YouTube video? You're going to be including 4 sections. So do the math. That's not a lot of time for each of these 4 sections. These 4 sections are going to correspond to the 4 sections we just talked about in the written report. Okay, and again, part of the grade for your oral presentation will be clarity of communication. You are going to be tempted to try and shoehorn as much possible information as you can in 2 minutes and 30 seconds to the point where when you present it orally here in class, no one's going to catch any of it because you're going way too fast. Clarity of communication. You can go back and review what we just said in the 4 sections. We're just looking for those things. Make sure those 4 basic elements are in this 2-minute and 30-second video. Okay, I'm not going to repeat those 4 sections. As a reminder, the 3rd section is arguably the most important one. This is the results section. You're going to have to convince us in probably about 45 seconds or less that evolution occurred, and that A is better than B, or B is better than A, or there's no difference. In a video, there's a much better way to convince us of this quickly than a fitness curve. Show us a video of an evolved behavior, and show us a video of a random behavior, and even better, show us the 2 videos and don't tell us which is which. If the evolved behavior is clearly better than the random behavior, all of us should be immediately able to see it in about 10 seconds or less, right? If you're evolving jumping, you know jumping when you see it. If you're evolving fast forward locomotion, you know it when you see it. If you're evolving pronking, we'll know it when we see it. Yeah? So like in the written report, during this section, you're trying to convince us visually that evolution actually worked. The evolutionary algorithm was able to improve fitness. Better to show us with a video than a static plot. Okay. Same thing when you then try and convince us about A and B. Show us another pair of videos, which is your best evolved A and your best evolved B. If you're trying to convince us that A evolved to move faster than B, again, we should be able to see it. If we see a quadruped that's moving visibly faster than an evolved hexapod, we should be able to see that in about 10 or 15 seconds, and you've convinced us of that fact. If you have any time remaining in your 45 seconds for this section, show us a visualization to further convince us. Like Darwin, kill us with data. Show us as much data as you can, but try and keep the verbal explanation as short as possible. If you're verbally racing through these 45 seconds, we're not going to be clear on what we're looking at or what you want us to take away from your videos or image. Make sense? Okay, this is kind of the core of your contribution in your final project. We're all clear? Okay. All right, when you shoot this video, make sure that there is no sound, because when you submit this silent video Monday night, Tuesday morning, you're going to get up here in class, in the front of the class for 2 minutes and 30 seconds, and you're going to verbally narrate over your video. There on the left, you see the random robot behavior. Here on the right, you can see the evolved behavior. Now you can see an evolved A on the left and an evolved B on the right. And as you can see, B evolved to jump higher than A. That's what we're looking for in the oral presentation. Okay, when you're making this video, by now you've obviously created a lot of videos, but you might be composing multiple videos and multiple images into your 2-minute and 30-second video. Lots of screen capture and video creation software out there. I like OBS. It's free, it's platform independent, and it's relatively easy to use, but we don't care. Use whatever you like. No points will be deducted for poor video. If you end up recording everything on your phone and stitching the videos on your phone together into a 2.5-minute video, that's fine. We're not giving extra points for production quality here. But if you do, just make sure that the quality of your video is good enough so that we can see whatever it is you want us to see in the video. If you're trying to show us that B jumps higher than A, make sure the video quality is good enough that we can actually see that. Remember that we're watching this video on this screen, and some of you are going to be sitting in the back row, so make sure things are large. Don't create a video that takes up this amount of real estate on the screen. Those sitting in the back are probably not going to be able to see it. Make everything big. If you do print any text on the slides, make it big. Make it big. Okay. All good? All right. By 11:59 p.m., upload it to YouTube, make it public, not for kids, whatever it is. Make sure that when we click on your link in Brightspace, we can see your video. You're going to upload your video to YouTube and then copy and paste the URL into the Brightspace submission. Our long-suffering teaching assistant, Freya, she is going to, after midnight on Monday, start to stitch all of these 60 videos into one long playlist. She's going to do this between midnight and 7:30 in the morning on Tuesday. Freya is going to be very tired at this point. Her attention span is going to be relatively low. When she gets to your name in the list, and if she doesn't see your submission in Brightspace, she's going to leave a blank slot in the playlist and go on to the next one, and you will receive a 0% for your oral presentation. So there is no late policy for submission of the oral presentation for obvious reasons. You all heard that? Okay, all right. All right, that's Monday night. Let's talk about Tuesday morning. All right, come to class, 7:30 a.m. on Tuesday. I will bring donuts and coffee. You bring your ability to narrate for 2.5 seconds over your YouTube video. Fair? All right. I will post Tuesday morning. I will post on the schedule, and I will also write it all out here on the board, who is presenting at what time. Please come to class at 7:30 a.m., assuming that you may be the very first one to present, because you may be the very first one to present. If you are the very first one to present, please do stay for the entire 2 hours and 45 minutes. There will be free coffee and donuts for you. Please do your fellow students the compliment of staying, watching what they've done. All of you have done some really amazing work. I promise you there are some hidden gems in these 60 final presentations. You're going to want to stay to the end and see all the great work that your fellow students have done. Okay. At 7:30 in the morning, I am going to press play on the playlist that Freya is going to create, and then we are not going to stop the playlist. The playlist is designed to run for 2 hours and 45 minutes. Don't worry, Freya will build into the playlist 2 10-minute breaks at the hour mark and the 2-hour mark. Fair? Okay. We've done this several times now, but it requires all of us to do exactly what's written in this document so everything runs smoothly. The train is going to leave the station at 7:30 in the morning, and if you're not on it, you're not on it. Fair? Okay. All right. Like I said, I will make the oral presentation schedule available. I'll embed it in the course schedule and write it up here on the board for Tuesday morning. Again, we're not going to stop the playlist. So when the student before you in the list starts speaking, Please come up to the front of the room and stand on the far side of the screen so you're immediately ready to go. When the student standing here finishes presenting her 2-minute and 30-second oral presentation, she will come around this way, sit down. The next speaker will immediately come here and start speaking as his video immediately starts to play. We are not going to pause the playlist. Fair? All right. Okay. Like I said, in order to keep on time, videos will play one after the other with no pause in between, 2 10-minute breaks. This means when your video starts, you should start speaking immediately. If you run long, I'm going to bring a long hook and I'm literally going to pull you. No, I won't. But if you run long, I will cut you off so that the next student can start. So practice, practice, practice. You only have a 2-minute and 30-second video. So in 20 minutes, you can practice 8 times in a row. It won't take you long to memorize your narration. Get it down pat, watch yourself with the clock, and you'll be fine. Years ago, I was invited to give a talk at MIT. The talk was 30 seconds long, and they put you up on stage, and they shut off the mic and shut off the lights after 30 seconds, after you were done. So I practiced my talk on the 3.5-hour drive down to Boston with my long-suffering wife in the car. She had to listen to this presentation every 30 seconds for 3.5 hours. This happened about 15 years ago. If she was here, she could probably narrate it for you verbatim. Practice, practice, practice. It won't take you long to memorize it so that you can keep to exactly 2 minutes and 30 seconds. Okay. Again, I wish we had more time, but we don't. So due to time constraints, if you have a question about one of your fellow students' presentations, please go up and ask them your question during the breaks or after the final presentations end. You're all suffering through physics engines and evolutionary algorithms and robot neural controllers. You should all compare notes. Please do chat about what worked and what didn't work amongst yourselves during the breaks and after the presentations. All right. Final point here, which I probably shouldn't even have to mention, please practice collegiality during this time. There will be a temptation to tune out. 2 hours and 45 minutes is a long time to sit and listen to presentations. I know you're all going to be very tired next Tuesday. You've got a lot of other demands on your attention. You've all put a lot of work in it, a lot of creative work, so please practice collegiality, extend your fellow students the respect they deserve by watching and engaging with their presentations by asking them questions after. And please do stay until the end. Okay, any questions about all that? Crystal clear on what we're doing next week? Okay, great. All right, so back to the last 2 lectures of the class, lectures 24 and 25. We're working our way through the final theme of this course, where we're looking at investigators that broadened their evolutionary algorithm so that evolutionary algorithm was optimizing various aspects of the physical structure and neural control policy of the robots. We looked at Carl Sims's work way back from the 90s. On rigid robots. We got partway through lecture 23 last time, looking at evolving bodies and brains for soft robots. We ended last time by talking about the physics underlying the particular soft-bodied simulator that is used in the experiments we're about to see, and this is Voxcraft or VoxCAD. Just as a reminder, everything we're seeing in the simulations we're about to see are a whole bunch of collections of cubes inside pairs of neighboring cubes. They are connected by a spring, or if you like, you can think of it as a semi-rigid beam. Each beam has associated with it 2 sets of 3 tuples, 2 sets of 3 numbers. The first 3 numbers describe how the spring or the beam resists pushing and pulling, shearing, pulling, or pushing and pulling forward and back. 3 numbers that are determining how the spring resists changes in x, y, and z. between the pair of cubes that are attached by that spring. That's linear stiffness. Linear stiffness. The k sub phi here are a second set of three numbers that dictate how that beam or that spring resists yaw, pitch, and roll. The pair of connected cubes twisting or rotating relative to one another. We can set for any one of these beams those 6 numbers to make it more or less resistant to any one or more of those 6 numbers. Everybody see that? So you could have, for example, one pair of cubes attached by a slinky, something that basically allows the 2 cubes to move almost completely independently of one another. And simultaneously, inside the same soft robot made up of all these cubes, this cube and this cube could be attached together with a steel girder, something that completely resists or almost completely resists any change in position or orientation of the connected cubes relative to one another. So coming back to the simulation here, what are you seeing here? Among the red cubes and among the blue cubes, tell me about linear and rotational stiffness. You obviously can't see the beams, let alone the actual parameters associated with these beams. What's going on here?
It looks like the darker colors have higher stiffness.
The darker colors. The blue in the middle has higher stiffness, and the red ones are connected with stiffer beams or springs. Everybody get how this physics engine works? Okay. All right, you can play around with it. We set up a website for it. This is sort of the modern version of VoxCAD, now called VoxCraft, because of course we need to nod to Minecraft here. It's got a relatively easy to use front-end user interface. You can actually interactively construct a robot, so no evolutionary algorithm here. You can manually drop cubes into the simulation. Let me speed it up a little bit. You can see someone creating a bunch of connected cubes here, and they've chosen a particular color on the right. The color is telling the simulator how to connect pairs of connected voxels, how strong or how weak to make the beams that connect pairs of connected cubes. You can see them laying down one layer after another. Red is flexible here, and blue is stiff. They're setting some other specific material properties of the simulator, of the robot. Okay, now they're going to simulate the behavior of this robot in the physics engine. Tell me about the controller inside this robot. We haven't said anything about the controller yet. We've only been talking about how to simulate the physical structure of this robot. You're all now experts in neural control of robots. What do you think's going on inside this robot? How is it being controlled? There's some volumetric oscillator. We've seen lots of oscillators now in the neural controllers of these robots. Those oscillators are also known as CPGs, central pattern generators. So this is open loop control. There is a sinusoidal pattern that is being fed into this robot. No sensors. And as Cam just said, there's some volumetric change. So we've seen a lot of robots now with rotational joints. We've seen wheels. We've seen little rockets on the Space Invader robots from Minimal Cognition. Now we're seeing a different form of actuation. There are some forces being applied inside this robot that are causing volumetric changes in this robot. What's going on here, do you think? We've got this sinusoidal pattern that's going up and down. What is going up and down? When we saw actuated rotational joints, up and down meant flexion and extension. When we looked at wheeled robots, higher or lower numbers meant a faster or slower spinning wheel. When we saw the rockets, higher or lower numbers meant more or less force being emitted by the rocket. What does higher or lower mean here in the central pattern generators?
I'm guessing higher is expanding and lower is contracting.
You're getting there. Expanding and contracting of what?
The springs between the voxels.
Bingo. So in the user interface, it looks like it's drawn so that it looks like the cubes themselves are increasing and decreasing in volume. That's just sort of the visual representation of what's actually going on under the hood, which, as you said, is those values in the CPG are setting or changing the resting length of the springs. That's one more detail of springs I don't think we've mentioned yet, or we might have mentioned in passing. Springs have stiffness, they have damping, they resist pushing and pulling and twisting. Springs also, physical springs also have a resting length. If nothing is pulling or pushing or twisting on them, they will come to rest at a default length. I should have brought an actual spring with me today. If we just put it on the table and measured it, it would have a length. That's its resting length. If we take a spring and cut it in half and put a little piston in the middle, and that piston can expand and contract, we are in essence increasing or decreasing the resting length of the spring. So in the robot you just saw in the video, the CPG is increasing or decreasing the resting length of the springs that connect neighboring voxels together. That's how actuation occurs in the soft robots that are simulated in VoxCAD. Everybody see that? Okay. Okay, so now let's have a look at some actual experiments. As always, we're going to look mostly at simulation. But we have actually done some recent work, it's only a couple of years old now, where we actually built a physical version of some of these evolved soft robots. In the physical robot, hopefully as you can see, there aren't springs or beams connecting neighboring cubes together. These are actual soft hollow cubes. I have two of them in my office on the other side of this wall, and of course I forgot to bring them to class this morning. My apologies. Hopefully you can see from the images here, these are soft, hollow voxels. They're just filled with room temperature air. They're made from silicone, so soft rubber. They're a little bit softer than a bicycle tire, basically. You'll notice there are some tubes that are coming out of a couple of these voxels. This is the resting state of this little 1, 2, 3, 4, 5 voxel robot. We are neither pushing air in nor pulling air out of this or this voxel. This robot is at rest. Same robot a few seconds later. Off to the side, there's a little hand pump that a graduate student is holding, and they are manually pushing air into these voxels in exactly the same way that you pump air into a bicycle tire. Nothing fancy here on the engineering side. Here we are pulling air out, and you can see that the voxels decrease in volume, and they also buckle a little bit. It becomes very quickly a relatively complicated physical material. Not easy to cross the sim to real gap here. We're working on it. Okay, so here's simulated softbots. We've just talked about how we simulate them. And here's how myself and my colleagues are trying to instantiate them in reality. Ongoing work. Okay. Here's an attempt to build the quadruped that you all are familiar with now. We can't seem to rid ourselves of radially symmetric quadrupedal robots. You'll notice that there is, hopefully you can see there's just one cable coming off here. There is one grad student, one cable who is pulling and pushing air into this thing. And you notice that more than one voxel is expanding and then contracting in volume. How? What's going on here? What's going on inside the robot, do you think?
Are the individual voxels connected to each other so they flow through?
We got a hole punch, and when we started to put all these voxels together, we punched holes in a few of them, took two voxels that had facing holes, a little bit of epoxy glue, and stuck them together. So this robot has a vasculature system. When it inspires, when it pulls air into itself, or it has air pushed into itself, that pressurized air starts to flow through some of the holes in neighboring voxels. They don't all have a hole in them, but where there is, that pressurized air flows through the body of the robot, and you see it almost literally breathing. It's not enough pressurized air to get this thing to move. Again, we're working on it. Okay. I will show you this sped up video here. What you're going to watch is an attempt by my former PhD student, Sam Kriegman, to actually make one of these physical soft robots from scratch. He just poured what's called dragon skin into that cup. It's liquefied silicone, which at a higher temperature starts to set and solidify. Here he is pouring some of this dragon skin, or this silicone soft rubber in its liquid form, into this little mold. He's going to cook it for a little bit. It's now heated up. The pink dragon skin that's in the mold has solidified. He's putting in a little bit more liquefied dragon skin. Spin it around a little bit to evenly coat the 5 faces of each of the wells in this mold. X-Acto knife, now that the silicone has solidified, he's going to cut them out, and we're going to have a whole bunch of cubes that have 5 of their 6 sides. He's gluing them together, and we're now going to hole punch. He already hole punched a hole connecting some of the, connecting some of the neighboring voxels together. So here's Sam creating the vasculature system for this soft robot. Take a little bit more liquefied dragon skin, silicone, create an even layer of it. And now he's going to create the 6th face for these 4 voxels. Add a little bit more for good measure. Release it from the remaining dragon skin, put a little air tube inside, seal everything up with more dragon skin, which solidifies into soft rubber silicone. Put a few valves on, and there you go. I will play the last bit again, slow down. Oh, sorry. And it walks, kind of. Okay. If you go to the Voxcraft website, you too can build physical soft robots. All of the materials to do this cost about $150. You can get them all from Amazon. So if you're looking for a do-it-yourself project this summer, there you go. Okay. All right. So assuming we can evolve soft robots and then in the not too distant future, successfully transfer them to reality, why would you want to do it? So let's have a look at the evolution of soft robots now. Professor Cheney here, this is some of the work he did as a graduate student. We just talked about the final project and demonstrating, or how to demonstrate whether evolution has occurred. Here you go. Among these two GIFs, which is the evolved robot? Hopefully you can see it's the one on the top. You'll notice that whatever this evolutionary algorithm is doing, it's able to alter the 3D geometry of the robot. It's placing some voxels in different positions, and you'll see some of the voxels have different colors, which is always a reminder that the underlying beams connecting those pairs of neighboring voxels together are stiffer or softer. So color represents material properties. Okay, how do we actually do this? Nick used this particular kind of neural network that you see on the left to paint the 3D geometry and material properties onto these voxels. What kind of neural network is this? It's a compositional pattern producing network. You'll remember we introduced CPPNs, which create a phenotype. This is the genotype over here, is the phenotype over here. In this case, we want to paint a pattern into three-dimensional space. So we have this empty cube. We visit a bunch of points inside this cube. And in this case, there are two output neurons for the CPPN. The first output neuron, whatever that value is, we round it to a value that's either 0 or 1. So the first output neuron from the CPPN is a binary output neuron. As we visit each point in this cube and feed in the x and y and z coordinate, we'll ignore the d here for our purposes today. We feed in x, y, and z. If the value that arrives at the output neuron is 0, we don't place a voxel there. If we visit a point inside this empty cube, we feed in its xyz coordinate, and the output is a 1, we do place a voxel there. So this CPPN is going to drop voxels inside this empty cube to construct the 3D geometry of our soft robot. While the CPPN is dropping cubes, the second output neuron is rounded by an activation function that rounds that value to an integer that is either 0, 1, 2, or 3. There are 4 possible values for the second output neuron. We are going to paint one of 4 colors onto each dropped voxel. And those 4 integers are dictating the material properties of that cube. More specifically, that value is dictating the stiffness or softness of the beams that connect that voxel to whatever neighbors that voxel has. So far, so good? Okay. So the evolutionary algorithm that you're going to see in a moment, Nick started by creating a population of random CPPNs with different cognitive architectures, different synaptic weights. He took each one of those CPPNs and allowed it to construct something like this, and then took that structure and dropped it into VoxCAD, which simulated how well that soft robot did at moving from left to right. That should be pretty familiar at this point. Okay, here we go. All right. What you're going to see in a moment is a visual representation of what these 4 colors do. I'll just pause this here for a moment. Okay. Let's look at the blue ones. So the light blue here is called soft support. So these are soft voxels, which means any of the beams or springs that leave a light blue voxel do not resist pulling or pushing or twisting by its neighbors very much. This is passive and soft material. This is not unlike fat or other passive soft tissues in your body. They are pulled and pushed by other things in the body of the soft robot. Dark blue voxels here are hard support. These are voxels, every dark blue voxel that you're going to see in a moment, all of the beams that leave dark blue voxels, those beams strongly resist any pulling and pushing by neighboring voxels. Red and green voxels, they have medium stiffness, but they also contract and expand. In this case, the CPGs that are going to exist inside these soft robots, the CPGs are changing the resting length of the beams leaving the red voxels, and the CPGs are also altering the resting length of the green voxels. Sorry. You'll notice that the red and green voxels, whenever a red voxel gets bigger, a green voxel gets smaller, and alternatively, when a green voxel gets bigger, a red voxel gets smaller. So red and green are both muscle, but they're increasing and decreasing in opposition to one another. We've actually seen that idea already in this course. What is that? It's a type of bioinspiration here that's coming from a particular detail of muscle physiology that we've already talked about in this class. Anybody remember? Where did we see this before? Do you remember the anthropomorphic arm that was trying to distinguish between spheres and elliptical objects? What do you remember about the muscles inside that arm? There were 7 joints inside that arm, but there were 14 motor neurons.
It's just like the muscles could only pull, so they were in opposite directions.
Muscles can only pull, so if I want to push or extend my arm, how do I do it? That's agonist and antagonistic muscle groups. So you can literally see when the red and green voxels, when one of the red voxels is increasing in volume, it's pushing against its neighbors, and at the same time, any green voxels are going to be pulling on its neighbors. So Nick made available to the evolutionary algorithm the ability to create agonist and antagonistic muscle groups if it's helpful for the task of evolving soft robots to move from left to right. Here are some examples of evolved robots. Here's one with dark blue, which is bone, and light blue is passive soft material. There's red and green, so you can see agonist and antagonist. There's red and green again, agonist, antagonist. There's just one giant ball of muscle. No bone, no soft passive tissue. Obviously, the fitness function here was to evolve locomotion from left to right. Let's actually watch one single evolutionary run. Here's the best CPPN in the initial random population. Here's the best CPPN at the second generation, best CPPN at the third generation, and so on. You'll notice as we move forward in evolutionary time, we're jumping from generation to generation, and we're seeing what pattern the most fit CPPN in the population is able to paint at that point in evolutionary time. What's happening? Aside from producing a very entertaining show reel of robots here. What observations can you make about the evolutionary process, at least in this run?
Seems to be just turning into all muscle tissue.
Perverse instantiation? Kind of. The task here is to move from left to right as fast as possible. If you can be built from muscle, bone, and soft tissue, you might as well just be a ball of muscle, generally speaking. You'll see there are a few solutions that still retain a little bit of bone, passive, stiff material, the dark blue. Some of them actually do rely on soft tissue here, the light blue. But most of the time, it seems, the evolutionary algorithm converged on big balls of muscle. You can see the usefulness of agonist and antagonistic muscle groups here. It generally makes sense that when one part of your body is pulling, the other part is pushing, or at least when one part is contracting, the other part is expanding. Okay, so that's how, or at least one way, to evolve soft robots. Why would we want to, let's switch from the how to the why. We saw one reason why you might want to evolve or automatically design and deploy soft robots last time. Soft robots can often get into places that are difficult or impossible for rigid robots to get. So there's a very boring, clear, obvious engineering reason to make soft autonomous machines rather than rigid autonomous machines. But there may be other less obvious reasons why you might want to make soft rather than rigid machines. Here was an attempt to demonstrate one of those more subtle reasons why soft robots might be advantageous over rigid robots. You might remember a rigid robot from a few lectures back, the evil starfish here. If we eventually want to deploy autonomous machines here in the real world that work literally alongside people, those machines better be able to handle surprise well. When they inevitably encounter something they never saw during evolution or during training, you want them to be able to adapt quickly and easily. You don't want them to do something completely unexpected. In the case of the rigid robot, when something unexpected happens, like for example, physical injury, it loses one leg, there's one and only one way in which a rigid machine can adapt to that kind of surprise. What is it? You're a rigid machine and you suddenly lose one of your 4 legs. What do?
You have to retrain.
You retrain to move in a different way. Yeah? Okay. For organisms that are unfortunate enough to lose a tail or lose a limb, they have other options available to them. What are they? They don't necessarily need to retrain to figure out how to hobble along on less legs, although that is still an option. There's an additional set of options if you're made from soft materials. What is it? Not so obvious, right? It's not something actually that humans do very well.
You readapt your structure.
You readapt your structure, not just your brain. You don't necessarily retrain your neural controller to move in a new way. You can also adapt your physical structure itself. What are some examples of that? How can you adapt your physical structure? What's the most obvious way? You lose a limb?
Grow it back.
Grow it back. We don't do it that well, at least not in our human form. There is an eye-opening set of studies about children, very young children that unfortunately stick their finger in a fan and lose the tips of their fingers. Below a certain age, they grow them back. So humans are capable of a little bit of regeneration, but not that much. So this is a little bit of a digression, but from a soft robotics point of view, if something truly unexpected happens to a soft robot, it has more options available about how to readapt, to deal with surprise. They can adapt their control policy, they can learn how to move differently, or they can adapt their body, or both. So in this particular study I'm going to show you here, that was the question we asked. If we create an evolutionary algorithm that can alter body or brain, and we then injure a 4-legged robot, like cutting off half of one leg or cutting off all of one leg, what does evolution do? Does evolution leave the body alone and retrain or re-evolve the controller? Or does evolution change the body? Or does evolution do both? Here's a robot that's been cut in half. Here's it running its pre-injured controller. Doesn't move very well. That's kind of the best this robot can do. That's a pretty severe injury if you lose half your body. Oops, what happened here? Sorry, where did we get to? Okay. Okay. There we go. Okay, here's a four-legged robot that's going to suffer arguably an even more grievous injury, which is we're going to cut off all four legs. And after cutting off all four legs, the evolutionary algorithm can adapt the controller or the body. Evolution chose, in this case, to regenerate the lost legs, at least as best it could. Not that that is necessarily the best thing, not necessarily that's the best thing to do, but again, if we want to create capable and safe robots here in the real world, we want to give them as many options as possible to recover from the completely unexpected. Not surprisingly, if you're a soft robot, it involves the ability to regenerate. Here's a different strategy. In this case, again, we cut off half of the robot's body. After seeing the previous version of the previous video, we felt pretty confident what we would do, what the evolutionary algorithm would do in this case. It would either figure out a way to retrain this controller to get this two-legged robot to move, or the evolutionary algorithm would figure out how to expand some of these voxels to quote-unquote regrow back the two legs. It's obvious what it's going to do. Thinking about thinking is misleading. In this case, the evolutionary algorithm chose to retract the remaining two legs and revert to away from legged locomotion to an earlier form of locomotion, which is, remember our discussion about locomotion? Mother Nature's preferred way of evolving strategies for organisms to move from point A to point B. Peristalsis. What you're watching is actually the same neural controller that controlled the four-legged robot. So the evolutionary algorithm found that it doesn't actually need to change the neural controller at all. All it needs to do is permanently change the resting length in the feet to retract or shorten those beams, and that produces a worm-like body, which the controller that was previously producing four-legged locomotion in a four-legged machine, that controller now produces peristaltic motion in an anguilliform or worm-like body. For us, at least, this was a very confusing result about the interdependency between body and brain.
From a technical standpoint, are you allowing it to change the material that every box is using when it's adapting to the injury?
Yeah, great point. No, we didn't allow it to stiffen or soften the material, but it would be great to redo this experiment in that case. The only option available to the evolutionary algorithm was tune how the CPG affected the voxels, the increase and decrease in voxels, or change the permanent resting length of the springs. Make some of the voxels permanently smaller or permanently bigger. Okay, so just our contribution to the thought experiment about why we might want to create soft machines. Okay. A couple other just sort of smaller experiments I wanted to demonstrate. When we created this soft-bodied simulator, we redid an older CPU soft-bodied simulator, redid it for GPUs, which allows us to simulate a very large number of voxels. Once we had a GPU-accelerated soft-bodied simulator, we asked ourselves, what could you do if you could make a robot from a very large number of voxels? I don't think we're very imaginative. For us, it's always quadrupeds. In this case, it's quadrupeds all the way down. You can go check out some of our other fractal robots on fractalrobots.github.io. Again, aside from the answer, because we could, why might you want to evolve fractal robots? Here's our attempt to answer this question. You'll notice on the left, we definitely have not worked out all of the kinks in our soft-bodied simulator here. In this case, we are evolving bodies and brains for robots again. We're setting the 3D geometry and the material properties of this little robot here. The fitness function is to move from left to right, as always, in this form. But we evaluated each genotype twice. The genotype is a CPPN that produced this phenotype. We measure the fitness of this phenotype of this robot. Then we take the same CPPN, the same genotype, allow it to rebuild this structure, but put that structure together in the same way. And how well does that fractal version of this robot do at exactly the same task, which is move from left to right? In this case, you can see that this particular CPPN doesn't do a very good job. It discovers a robot that does well on its own, but when it's fractally composed, it does not do very well. Here is a second fractal robot. A different genotype, a different CPPN that's going to paint a soft robot, which again you see on the left here. And then the way in which that CPPN paints individual voxels, we ask it to paint the same structure again, but now instead of painting with voxels, it's painting with this. This is a robot that is made up of these robots in the same pattern. And we get a little bit of a better result. It's not ideal, but that same robot has the same structure at one scale as it does at a different scale, and it has similar behavior at different scales. So this robot is structurally self-similar. It has the same structure at different scales, and it is functionally self-similar. It does similar things at different scales. Make sense? Again, aside from the fact that you can do this, why might you want to do this? Why might we want to task evolutionary algorithms with designing fractal robots? Robots that can be structurally composed together in similar structures at different size scales, and when you do, they do the same thing.
I mean, my thought would be for modularity's sake, because if one of them gets damaged, you just slot in another one that's identical.
Yes, that's part of the answer. It's kind of modular. We've got a whole bunch of these things and we can slot them in. But why specifically do we want structural and functional self-similarity, do you think? Why might this be useful?
Could it be like real-world manufacturing?
For real-world manufacturing, why is this helpful for real-world manufacturing?
Well, if it's a repetitive pattern, it's easier to make.
If it's repetitive, it's easier to make. So as long as everything's made from the same small set of parts, much easier and more cost-effective to build. But how does this help us with, again, the long-term vision of making capable and safe machines here in the real world?
One of them breaks or falls off, and it's still
Oh. We're getting kicked out. Say that again, a little bit louder.
If one of the parts breaks off, you still get the net.
You get the net behavior if one part breaks off, kind of, but specifically why fractal?
You could reconfigure them and have the robot do something else.
You could reconfigure them and have them do something else. In this case, we're after the opposite. Configure them in the same way over and over again to make a bigger and bigger robot, and it keeps doing the same thing. If we can get evolution to design a small robot that cleans up all the garbage here, maybe we can put 100 of them together outside and clean up all the garbage on the quad. Do the same thing, clean up random detritus, but at different size scales. Who knows? We'll see. Our final class on Thursday, we will talk about xenobots. You have a quiz due tonight. You're working on your final project. See you on Thursday.